The significant figure convention is a convention that we're going to be using all year in general chemistry to report the uncertainty associated with measurements or calculations based on measurement. And we're going to spend some time learning how to recognize significant figures and apply the significant figure convention to calculations in this lecture. The first step towards understanding the significant figure convention is understanding the difference between exact and inexact numbers. Exact numbers involve numbers like pi, which are mathematical quantities. It involves definitions. So definitions, when we define 1 foot is exactly 12 inches. That's a definition. We don't mean 1 foot is about 12 inches, give or take 1/10 of an inch. It's exactly 12 inches. Similarly, when we define 1 kilometer as 1,000 meters, that's exact. Again, there's no uncertainty associated with that. Another category that are considered exact are counts of items. So if I were to count, for example, 22 students in the room, that's an exact number. It's not 22 plus or minus 1/10 of a student, which makes no sense. It's either 22 or it's 23, and I assume that I can count them, so it's exact with no uncertainty. The uncertainty comes in when we make measurements. So for example, when we measure the mass of a quarter, it depends on what the measurement device is, how well we know that number. How long does it take for you to read all of the words on this slide? Well, it depends on the stopwatch you're using, the precision of the measurement device, how accurately you can start and stop. There's some uncertainty that is inherent when any measurement is made. Another category that always involves uncertainty is any calculation involving measured quantities. So that, for example, if I measure the length and width and height of a box and want to calculate the volume, how well I know the resulting volume is limited by how well I know those dimensions that I've measured with some sort of measurement device. So the uncertainty in the resulting number is inexact due to imprecision in the measurement device itself. When I make the measurement of the mass of a dime, for example, I can report it, as you can see here at the top of this slide. I measured a dime on our analytical balance, which is very precise. It has an uncertainty of 0.0001 grams. It's a very precise measurement device. That is what we refer to as the uncertainty. The uncertainty is a value with units that matches the units that we use in the original measurement itself, the 2.2403. Now it becomes very clumsy to always write plus or minus some quantity every time we write down a measured or inexact number. And so we use the following convention, and this is the heart of the significant figure convention. What we're all going to agree to do is to report inexact numbers so that the smallest digit shown has an uncertainty of plus or minus 1 in that digit. So instead of recording the mass of my dime as 2.2403 plus or minus 0.0001 grams, I just write it down as 2.2403 grams. And by stopping at that last digit, everybody reading this will understand that there's an uncertainty of approximately plus or minus 1 in that digit. And this is a much more convenient way of representing the uncertainty without having to write down lots and lots of digits every time. So let's just look at some practice cases where we can look at measured values and determine the number of significant figures and the uncertainty represented with the significant figure convention. So in our first number, 352 centimeters, there's never any ambiguity when the digits are non-zero. When they're non-zero, all non-zero digits are significant. So this has 3 significant figures, and the uncertainty determined by this last digit is 1 centimeter. In the second number, we see an example where we have a 0, but the 0 is in between two non-zero digits. Any zeros that are in between non-zero digits are always significant. So in this case, we again have 3 significant digits, and our uncertainty is 1 kilogram, as determined by the last place digit and the units on the original measurement. Now in this third example, we actually have a trailing 0 after a decimal point. The only reason to write down this 0 is to convey to somebody reading the number that I actually know this number to within plus or minus 1 in that smallest digit. Therefore, all 5 digits in this value are significant, and our uncertainty is 0.01 kilograms. This is a much more precise measurement. In the next example, 501.02, again, the zeros are enclosed between non-zero digits, so that makes them unambiguously significant digits. So there's 5. I use the word significant digit and significant figure interchangeably. And once again, the uncertainty is 0.01 kilograms. Now our next example, 0.002. In this case, the zeros here are placeholders that tell you the magnitude of the number. Notice that the 2 is the smallest digit. There's an uncertainty of plus or minus 1 in that value. This has only one significant figure. And another way you can see this is by recognizing that I could have written this number as 2 milliseconds just by picking a different unit, and I would have the same number of significant figures. So the uncertainty here is either you could write it as 0.001 second or equivalently as 1 millisecond. In the next example, because there's a trailing 0 after the 2, that trailing 0 after a decimal point always significant. So the significant digits are the 2 and the trailing 0. That gives us 2 significant figures. And now we have an uncertainty of 0.0001 second, or equivalently, 1/10 of a millisecond. Finally, in the last example, trailing zeros that are not behind a decimal point are actually ambiguous. It's unclear whether the person who wrote this down meant to convey that we know this number to plus or minus 1 meter, or do we only know it to plus or minus 100 meters? It's just not clear. This we call an ambiguous case. And we don't know what the uncertainty is. We could clarify this by writing it down in a different way. For example, if we use scientific notation, 1.30 times 10 to the third meters. Now, this 0 becomes a trailing 0 after a decimal point, and this would have 3 significant figures, the 3 digits in what is called the mantissa of the scientific notation. And it would have an uncertainty of 0.01 times 10 to the third meters, or we could write that as 0.01 kilometers. So there's examples showing all of the possible cases for counting significant figures and determining the uncertainty in the resulting value. Now let's see how to involve the significant figure convention in calculations. So if we want to find the volume of a box with the dimensions given in this problem, we have to use an equation of some kind. Volume equals length times width times height. So plugging the numbers in, I've got 12 centimeters times 113 centimeters times 6.205 centimeters. And if I just blindly plug this into my calculator, I get 8,413.98 centimeters cubed. But is this how we want to convey this information? Is it reasonable, if we only know the length to plus or minus 1 centimeter, that I could possibly report the volume to plus or minus 0.01 cubic centimeters? That seems unreasonable. So let's think about how this should be reported in this significant figure convention. The rule for multiplication and division is that when you're dividing or multiplying inexact numbers, keep the smallest number of significant figures in the final answer. So in this case, we've got 2 significant figures in this first number, 3 significant figures in the second number, 4 significant figures. You can see why counting significant figures becomes important. The smallest of those is 2 significant figures. So the way that we should report this is by rounding the number that we have to 2 significant figures. So we're going to report it as 8.4, and just to be clear with significant figures, I'm going to use scientific notation so that it's clear how many significant figures I have. 8.4 thousand cubic centimeters, or you could rewrite that as 8.4 liters, remembering that 1 cubic centimeter is 1 milliliter, and 1,000 milliliters is 1 liter. When we add or subtract inexact numbers, however, we use a different rule, and this is really important to remember and easily forgotten by students because most of the time we multiply or divide. But when we add or subtract inexact numbers, then we look at the largest uncertainty instead of counting significant figures. So if we were to write down the result of this temperature conversion that I have here, the answer would be 293.35 Kelvin. But here we have an uncertainty of 0.1. Here we have an uncertainty of 0.01. We keep the largest uncertainty between those two. And so when we round this, we would round to 293.4 Kelvin. And whether you round to 0.4 or 0.3 in this case, since the trailing digit is a 5, doesn't really matter. You can round up or down. As a second example, if we were to add 12 centimeters plus 6.87 plus this number, and we just blindly write down the number, the resulting number would be 132.595 centimeters. But here we want to keep an uncertainty of 1 centimeter, so we're going to round to the 1 centimeter place, and this is unambiguously a number that should be rounded up, since 595 is closer to 1,000 than it is to 0. In the proper rounding, this is 133 centimeters. And the biggest trick is simply to remember that we have a different rule for addition and subtraction than we do for multiplication. Finally, when you apply significant figure rules in a calculation, always remember to apply the rules at the very end of the calculation and not to intermediate results, because this leads to what we call round-off error. Repeated rounding several times in the course of a calculation can build up and lead you to the incorrect answer. So one way to avoid this is to enter the numbers all at once into your calculator. Use your calculator to keep the number to its full significant figures and round at the very end. So in this calculation, regardless of what it means, if I were to take 3.7 divided by 12.011 multiplied by 6.022, all of those are inexact numbers and lead to uncertainty. I'm going to round my final answer to 2 significant figures. If I write down my full answer as my calculator tells me, it says 1.855083 times 10 to the 23rd atoms. But here I should be limited to 2 significant figures by this first value. So when I round to my final answer, I'm going to round to 1.9 times 10 to the 23rd atoms. The point of this is just to show you how to round at the end, not the details of what this calculation means. We'll worry about that later. But don't truncate. Always round off, round up or down according to whether the number you're rounding is closer or to 1 or closer to 0.